Say we have very happily created 6 or 7 microservices and everything is going good. Now for a new use case that is introduced in the product, we have to talk to not 1 but 3 services together to compile the final response. So what is a good way of implementing this and supporting this kind of request coming in the future? A high level pattern that helps us do this is called API composition. In this video, we in depth talk about this super simple pattern to query microservices, see what it is, how it is implemented, and understand how it not only helps in improving the performance of our backend systems, but also improve the performance or the experience of our end users. And we'll conclude our discussion with going through the advantages and disadvantages of adopting this. But before we move forward, I'd like to talk to you about a course on system design that I've been running for over a year now. The course is a cohort-based course, which means I won't be rambling a solution and it will not be a monologue. Instead, a small focused group of 50-60 engineers every cohort will be brainstorming systems and designing it together. This way, we build a solid system and learn from each other's experiences. The course to date is enrolled by 600 plus engineers spanning 9 cohorts and 10 countries. Engineers from companies like Google, Microsoft, GitHub, Slack, Facebook, Tesla, Yelp, Flipkart, Dream11 and many more have taken this course and have some wonderful things to say. The coolest part about the course is the depth we go into and the breadth we cover. We cover topics ranging from real-time text communication for Slack to designing our own toy load balancer to ClickBuzz's live text commentary to doing impressions counting at scale for any advertisement business. In all, we would cover roughly 28 questions and the detailed curriculum split week by week can be found on the course page, which is linked in the description down below. So if you are looking to learn system design from the first principles, you will love this course. I have 2 offerings for you. The first one is the live cohort based course which you see on the left side, and the second one is the recorded course which you can see on the right side. The live cohort based course happens every 2 months and it will go on for 8 weeks, while the recorded course contains the recordings from one of the past cohorts as is. If you are in a hurry and want to binge learn system design, I would highly recommend you going for the recorded one. Otherwise, the live cohort is where you can participate and discuss things live with me and the entire cohort and amplify your learnings. The decision is totally up to you. The course details, prerequisites, testimonials can be found on the course page arpitbhayani.me/masterclass, and I would highly recommend you to check that out. I put the link of the course in the description down below. So if you are interested to learn system design, go for it. Check out the link in the description down below, and I hope to see you in my next cohort. Say we are building an e-commerce platform and we have 3 services with us: orders, payments and logistics. Say we want to get order details, and in this is a very super detailed, super granular order detail that we would want to get for a given order. So in this case, what we would have to do is, in order to get the order detail, we will have to talk to the order service. In order to know the payment status of that particular order, we'll have to talk to payment service. And in order to get the shipment, the information or the logistic information about that, we'll have to talk to logistics service about that. So here our one client needs to talk to multiple services to get the things done. Now this is a classic case of how would we want to query the microservices. So we have added 3 services, but our user or our client has to talk to them to get the response. So how are we querying them? So to query microservices, a very common pattern, a super simple implementation is API composition, right? So in API composition, what we do is we put a middleman. We put a composer sitting in between. The user makes a request to composer. This composer knows what to do when it gets a particular request. For example, user would make a request, get order detail. This composer would then talk to order service to get order information, would talk to payment service to get payment information, would talk to logistics service to get delivery status. This is super simple, super straightforward on what could have been done, but this is exactly what API composition is all about. Sitting or basically placing a middleman in your architecture to hide the complexities of the underlying systems is what this particular pattern solves for us, right? And obviously, do we have to implement this from scratch? Not at all, right? So what can we use here that would act as our composer? A very common component that solves this exact problem is called an API gateway. So API gateway is a classic example of a composer, and we typically place it behind or basically before all of our microservices. So this typically, or API gateway, is the first point of contact for any request coming in from the user. And then API gateway would decide where it would need to forward the request to, or send multiple requests to multiple services and get the response and whatnot. So API gateway is the one who would be doing this for us. And what all popular API gateways can we use? Two super popular good projects out there is, the first one is Krakendy, the second one is Con. Really good projects out there. Highly encourage you to at least explore them. Write a hello world on your local machine. That would give you a very solid understanding of that. If you are on AWS, then AWS API gateway. If you are on Google, if you are on Microsoft, they have their own corresponding services that serves as an API gateway, right? So anything that would give you an API gateway is something that you can use as a composer. You can also choose to write your own composer. No one's stopping you. But why to reinvent the wheel if you already have a good, robust solution in place, right? So what we do in our architecture, we place API gateway in front of all of our microservices, and request directly comes to API gateway. API gateway either forwards the request to API gateway basically forwards the request to multiple services, gets the response, merges them, joins them, and sends it back to the user. Okay. So this, but then when you get a request to your API gateway, how would it forward the request to the downstream services? So obviously you might think that, hey, if I would want to make a call to 3 services, I should be doing it in parallel, right? No one's stopping us from doing it in parallel. But here, this is very use case specific. It might not be possible to make all the 3 calls to the 3 depending downstream services in parallel. It is very use case specific, where we need to understand that, hey, do we have all the information to fire the queries in parallel? If yes, go for it. If not, do it sequentially. Basically, parallelize where you can, where every data that you need, it's there, and then you parallelize it. That's perfectly fine, but it's very use case specific, right? But in general, if we do it sequentially, pure sequentially, one after another, it would take a long time for it to execute. But it is okay. It is not computationally intensive as such, but it would take a slightly longer time to execute, but it has its own advantages. The second is doing it parallel. It's very tempting to do things in parallel. Hey, let me just fork out multiple threads at once, which would basically fire individual queries to individual services. I'll grab the response, merge them, and send it back. But what happens is, when you have excessive parallelism in your system, it would require a lot of resources of your machine. So in this case, it would consume a lot of resources of API gateway in order to do that parallelism, wait for the response, merge the result, and send it back. And especially with respect to parallelism, you have limited cores on your machine. So parallelism is always limited by the number of cores that you have. Although you may spin thousands of threads, but they would all be in waiting state. They would not be executing. So parallelism is very tricky. It would require a lot of resources on the machine. Plus, it would also require programming language support. Let's say if you're writing in Python, Python doesn't have threads, or Python doesn't have basically parallel threads. It has concurrent threads, but it does not have parallel threads because it cannot leverage multiple cores of your machine. So in such cases, it also depends on the kind of language that you choose to implement your composer. If you are going for a managed solution, they would have made the best decision. But if you are writing it on your own, keep that thing in mind on how would you want to structure it. Right. Now, let's talk about a very interesting thing. Although the discussion seems purely on the backend side of things, but imagine how this adds up to improving the experience, the user experience of our end users. So for example, if we did not have a composer in the middle, then what would need to do? Your client, as in the browser of your user, would need to make calls to 3 services: order service, payment service, and logistics service, to get that information, compile it together, and show it in your UI. This is very expensive. Expensive not with respect to computation, but expensive with respect to the number of round trips that your client machine has to, or the packet has to make from your client machine to server and back. So here your client would have to initiating 3 API calls to 3 services separately, wait for the response before it can render the page on its end. Now this is very expensive because from your device, which might be thousands of kilometers away from your server, it would take time for the packet to go there, then the server to compute the response and then fly back. It would take time for it to do it. So that's why you would always observe a higher latency when you are making a lot of round trips in your system. And then your client needs to be smart enough to understand the 3 responses and merge it. So although this looks, hey, let me just write 3 API calls on JavaScript and that would make a call, but it is not very efficient to do it. Plus, it would eat up a lot of data of your end user because you are making 3 API calls. So users' data would be eaten up. So how do we make the end user's experience better using Composer? So what Composer would do, because Composer is acting as a single point of entry, the user would make just one request, just one HTTP call from browser to Composer. Composer in turn would fan out to 3 different services, get the response, merge them or join them and then send the response. So this way your client only has to make one API call and done. Composer internally will do fan out and that is the headache of the Composer. Your client does not have to think about it. So it's better utilization of your client's data. It would have lower latency as compared to the first approach that we discussed. And there is just one round trip. So, and your client can be dumped to just understand what the response is and start rendering. It does not have to have the merge logic kind of stuff. Right. So this is where we, in general, when we talk about systems or we talk about microservices, we always think backend heavy. But this is a classic case on how a decision made in the backend positively influences the experience on the front end side. Right? So everything is a gigantic interconnected mesh. So whenever you are deciding something, see how it can impact basic possible things or the peripheral things around it. Right? Okay. So next part. One thing that I want to talk about is obviously this is not just one level of composition. Let's say we have a very complex logic in our system and we just simply said, hey, the Composer service will talk to order service, payment service and logistics service to get that information. But what if order service itself needs to talk to seller and inventory service to get its information? So here, this is multi-level API composition. The idea is, let's say your Composer sends a request to order service, but order service would need to talk to seller service and inventory service to get the order details. Could be possible. Right. So that's where you would see in a gigantic system, maybe a 10-year-old or 15-year-old e-commerce you would see this kind of pattern where Composer is not directly talking to all of the services. It's talking to few that it needs to, but that service might need to talk to few other services to get that information. Obviously, not very performant or not good for low latency application, but you get the gist that you might have to have multi-level API composition, something that I would not want to discard. Right? So multi-level API composition is a fact and we have to typically live with it, that in some cases when our architecture evolves or when our product evolves, we might see multi-level composition. Right? Now let's talk about advantages of API composition. Now this is where things starts to become very interesting. So advantages of API composition, first of all, we'll start with simple. Super simple to implement. We all see like just add one API gateway. It would take care of fanning out and basically gathering all the responses, joining them and send it back. Right? Pretty straightforward to implement. Second, user has a single point to interact. So because this is the first point of entry or the single point to interact, user only has to make one API call. It will internally fan out. So pretty solid, single point of interact. No smartness needed on the client side. Third, it hides the implementation detail and complexity. So your user made a request to your Composer. It does not need to know internally it is making call to 5 services, 10 services, 15 services, 0 services. It does not need to know. It hides and abstracts out the implementation detail. Otherwise, what your user would have had to do is it would have to call order service, payment service, and logistics service. Now it does not need to know. Everything is hidden behind the composer. So user makes a call to composer. Composer has those details, who should it talk to and get the response from, and then it would do the needful. Right. Fourth is security and limiting. Because we have a single point of contact for our user, so this is where, or on the composer side or on the gateway side, we can implement security, limiting, caching, and whatnot. Right. So this becomes our first line of defense. So every single thing around logging security, logging security practices, monitoring, whatnot, everything could be applied on this composer side. This way, what happens is, if we secure one, everything else is secured, right? So that's pretty neat way of ensuring your complete infrastructure security. Right. So that's where composer is again a very famous pattern to be implemented, because it makes life so simple for the internal teams. Next is it can cover bad design decisions and wrap them with a new interface. This is classic case. Let's say you had a very tight deadline, and you just randomly sent any response or any structured response without putting in a lot of thought into how are you structuring your response from one of your microservices. Let's say your payments microservices, right? The response is not ideal, not very good for your client. But then what happened is you made that bad design decision, and now something needs to change. You have to restructure your response because your front-end team is saying, hey, we can't work with this kind of response. We want a little simpler response so that it's easy for us to render the interface. Now, your bad design decision cannot percolate to your front-end team. So now what you do? Because you have a composer sitting in between, you can alter the response. There, you can restructure the response in your composer. Very commonly seen in high growth startups, you would see a lot of hacks being applied at your composer level. And that's how you hide your bad design decisions and wrap them with a very new shiny interface. Right. And the final thing, the most interesting application of this is, say you are trying to move out of monolith and breaking it into microservices. This is where composer plays a very important role. So now, because composer is great at hiding the implementation detail, say we have this monolith that we had, which is a legacy monolith, and the first service you would want to fork out is payment service. So what we'll do is we'll put a composer in between, forward any request that comes to /payment to payment service, and every other request goes to legacy microservices, to basically legacy monolith. This way, your user doesn't need to know that, hey, there is a separate payment service or there is a separate monolith service. And you can slowly keep forking out your monolith modules into separate microservices without impacting anything on the user side, but just by adding a layer of abstraction sitting in between. So this is a very common pattern that you will observe whenever you are planning to move from monolith to microservices or hiding out or abstracting out the complexities of transition. Very solid use case for that. Okay, now the final part. Let's talk about disadvantage. Obviously, again, as I always say, grass is not always green. Let's talk about disadvantages of API composition. First one, our composition or our composer is basically firing a lot of requests onto services, getting the response, merging them. What if the responses that it is getting from the services is huge? For example, hear me out. Let's say we are having a blogging application and we have a blog service, we have a comment service, and let's say we have a clap service. So for a particular blog, the blog service would have the entire blog page, blog details, everything that it would need for a particular blog. Then the comments is part of a separate service because it requires special kind of scaling. So comment is part of a separate service that we have, and clap service. Now let's say you want to fetch 10 blogs of a user and you want to render all of them with body, everything. Now this is a case that would be very heavy because it requires heavy amount of data transfer. You'll say, array, it's just blog. How long would it take, or how big the data would be? Imagine every blog is 2000 words. Right? These are essays. Like blogs is still small enough. These are gigantic essays that folks have written. Imagine Wikipedia pages. So dense in information. Right? So imagine these are all Wikipedia pages. Now what would happen? You get Wikipedia pages, a lot of comments on those pages and collabs that have been made there, and you gather all of that information. Like it might even go to half a MB size at API gateway. So API, and because what happens, you send a request, you get a response, everything is happening in memory. Your API gateway's memory will be full very soon, and it will start to choke, and it might even crash when it runs out of memory. So that's where when you are transferring large amount of data, or when you are merging large amount of data, you have to ensure that your API gateway is scaled enough. And if it you have written, or if it is you who has written Composer, you have to ensure that it is well written and basically at best efficient. Right? But if you are doing large, or if you are joining large data set, this is very expensive. Second is your overall availability is challenged. Here we can very clearly see that when the request comes to our Composer and it goes to 3 of the downstream services like blogs, comments and collabs, what we know is our availability is challenged. If one of those services is down, we are not able to compile the response. Right? So even though your comments and your collab service never saw any outage, but if your blog service is down, right, your end user is not getting the correct response, or your end user is not even getting the response, right? So that's where unknowingly downtime of one service had an impact on your end user, which impacted the overall availability of your system. Plus, what would happen is, as you have large number of services that you are talking to from your Composer layer, your Composer needs to manage and maintain a lot of state, who or which services where and how to connect to that, and how to get the how to send the request and get the response and whatnot. If you have large number of services there, or if you're talking to large number of services in one request, it would add up to a lot of load onto your API gateway, which might turn it into a gigantic bottleneck which you can't get rid of. So whenever you are adding, which looks like a single point of, it is not a single point of view, but it looks like a potential bottleneck, be always wary of the fact that availability will be at stake. Not that big of a challenge given that we have managed services, but still something to always think about when you're designing an architecture. Next is when your user is sending request to one, let's say API gateway, and it is forwarding request to 3 services. What you cannot get, or it is extremely difficult to get, is transactional data consistency. For example, you are storing some information and you want that the information is stored in blogs, comments and collabs, all the 3 places, or none. So doing that all or none across services is challenging. That's where you need distributed transaction. I already have a video on how to implement distributed transaction. I'll just link it in the iCards. Go through that. Go through that if you don't know how to implement distributed transaction. It would really help you understand, like, it's not just theoretical, practically we also do it. So coming back to this use case, that if you need strong data consistency, or if you need rather transactional data consistency, it is very hard to get it when you have multiple microservices behind an API gateway to get that information, right? Because your API gateway need to maintain or have to do the transactional part. It's very hard to do it at scale. So be wary of that fact. Next is Composer needs to be managed and maintained. We added one more component in our system, which is your Composer or your API gateway needs to be managed, maintained, observed, alerted and whatnot. Adds up to that part. Even if it is a managed service, you'd still need to monitor it just to ensure that if it goes down, you know the backup plan for that. And the final thing is your Composer may become a bottleneck. Again, not a single point of failure, but a bottleneck. So if you are getting a large amount of requests coming to your Composer might choke, because we saw that if you choose parallel invocation, it might add up to, or it would require a lot more machine resources to compute that information. And in general, handling a lot of surge onto your single composer, maybe a few set of machines, might be a little taxing. So it has a potential of becoming a bottleneck. So that's where have the right set of alerting and monitoring place on that one component so that you ensure that you are not in the blind spot. You know if something would go wrong, you can mitigate it before it goes bad. Right? So something to always think about. Nice. So yeah, that's it. That's it from me for this one. It definitely looked like a very simple topic, API Composition, but it had a lot of intricate details to it. So I hope I added value. If you guys like this video, give this video a thumbs up. If you guys like the channel, give this channel a sub. I post 3 in-depth engineering videos every week, and I'll see you in the next one. Thanks a ton.